สวัสดีค่ะ Good afternoon ค่ะ so last week the material was about numbering system, right? Okay. Which is quite straightforward, I think, right? Have anyone look at the video clip, video lecture file, or are you here? Maybe some of you just study by yourself or just look at the video lecture files at other time, right? And be able to finish the exercise problems and submit them on time, right? Okay, so that the solution for the exercise would be available this week. Okay. And then now is almost the end of August, right? The first exam is coming soon. Do you know when? When is the exam for this one, discrete math? The exam schedule is already available. Have you checked? Our exam will be on September the 10th. Okay. So that's 2 weeks from now. It's Wednesday as well, but probably not in this room. It's handled by university. Okay, so you have to check your exam schedule, okay, and find out the room number. Because we have a large size here, so that we may have many rooms, exam rooms. So you got to know which one is your exam room, okay? This could be different from your friends, okay? And during the exam, you have to wear university uniform, okay? It's required. I will not be there. It would be proctor by other university staff. So uniform, KMUTT uniform is required. You can bring a jacket just in case the air, the room condition is, it could be cold, okay? The exam would be 3 hours. And detail of what would be in the exam would be discussed later on. Mainly would be what we have so far till next week. Okay, till next week. Today we will have covered the topic which is about the Boolean algebra, and then next week I like to switch to the counting, okay, counting technique, which is, I think it's chapter 6, which is a simpler material to cover. Instead of about the proof methods. That would be later after the exam. Okay, so that would be easier for you. Okay, so that means most of the materials that we have for the first exam would be very familiar to you, that you had them in high school, secondary school, okay, and then just a few more advanced topics will cover, not much. Okay, so now Let's see. Okay, the lecture today, like, it has quite a lot of information. Okay, that could be easy for many of you, but might be like not like that for some others, because it depending on your like background. Okay. And also we have exercise problems to work on, so that about the first half would be done and due today in class, okay, by 5 or 5:30. Okay, so that's about the first 8 problems. And problem number 9 in the exercise sheet about logic minimization, that would be the homework. Okay. But once you understand the materials, it would take just like maybe half an hour to finish the exercise problem. So you have enough time to do it today, okay, after we cover the lecture here. So here is chapter 12. Okay, we jump to chapter 12 in the textbook about Boolean algebra. And then there are 4 sections to discuss today. Okay, just like giving you the overview, okay, of like the fundamental concept there, right? So that so you don't have to worry that you haven't seen some of this before. Boolean function, that's about the main part, and then we'll see about the logic gates. We have seen that, okay, but more today, and about the minimization, simplification of the Boolean expression. Okay. So Boolean logic, right? We know that it's just about 0 and 1 or true and false. Right? True, false. Again, and then normally we use a binary representation. 1 for the true and false is 0. And then we have the or, just like logic, right? Or, just like as we see here. This is A or B. Okay, it's a logical sum. And A and B. Sometimes we just write it this way, AB. It means A and B. Which is a logical product, okay, Boolean product, okay, Boolean product and Boolean sum. So suppose that A is given equal to 1 and B is 0, suppose, then we are able to find out the values of this like function. Okay, consider like could be a function of A and B. This is another function. So 1 or 0. Okay, 1 or 0 is 1. Just like true or false is true. For the n, is 1 and 0 would be 0. True and false is false. Next one is like A and B and then OR with A or B, total complement, okay? This sign, be very careful. This means the complement, right? Complement or negation. Okay, so that substitute A with 1 and B with 0. Then we have 1 and 0, right? And then OR with 1 or 0, and then total complement. So 1 and 0 is 0, or 1 complement is 0, right? 0 or 0 is 0, right? Do we have the same result here? Okay. What about if a function, another function, right? Just A, A or B bar. When A is 1 and B is 0, then we got 1 or 0 bar or complement, okay, the same thing. So that is 1 or 1, 1 or 1, or Boolean sum. So the result is 1. We don't have 2, 3, 4, no, just only 0 and 1, right? True and false. Okay, we see more later on as well. We talk about Boolean sum, right? Boolean sum, summation. Example is here, like A plus B plus C, or A or B or C. And this is like A bar plus B bar, A bar or B bar, right? This one. This one is this one. The product, okay, we have here, this one is A bar and B bar. This is A and B bar and C bar. Okay, just we got to be familiar with the notation here and the terminology as well. And then this one, A bar and B bar. Can we write it like this? A and B and then bar here? Is it the same? No, right? It's not the same because the A and B bar here, by the De Morgan law, then this would be A or B bar, A bar or B bar, right? Which is not the same as A bar and B bar. So when you write, okay, the expression, be very careful if it's this one or this one. Okay, don't make the bar like ambiguous. If the bar is for just a single variable or for the whole variable, the multiple variable together, นะคะ. And then we see more detail here for the Boolean sum and the Boolean product. Like we can check out like this one by one. Just like we know that 0 is false. Again, 1 is true, right? So that false and false is false. 1, right? True and true is true. This one. But for the OR, it would be this one, right? 1 or 1 is 1. True or true is true. False or false is false. If we have true and false together, then the result is false. Right? This one. But if this is AND, right? AND operation, but this one is the OR. So the result is opposite is 1. When we have 1 or anything is 1. True or anything is true. Right? Okay. So that this can be simplified just like could be x. Okay, x could be 0 or 1. Then if x is AND with 0, anything AND with 0 is 0. AND with false, right? Anything OR with true is true. Anything, any value AND with 1, true, AND with true, then we just have that one, right? So that if, in this case, if x is 0, the result is 0. If x is 1, the result would be 1, right? So that's the meaning that we have here. That we're gonna use this later on, okay, in our Boolean algebra. X and x is x. True and true is true. False and false is false, right? So x could be 0 or 1. And then here, right? X or x, we just see that it's just equal to x. So when we have like multiple terms identical, they are identical, then we can just keep one and just remove the rest so that we can simplify, right, the expression. Or if we have this one, the result is 0. X and x bar, x could be 0. If x is 0, then x and x bar would be 0 and 1 is 0. If x is 1, we can check, okay, check for our understanding. X and x bar would be 1 and 0. That is 0. Okay. Always the same result. The result is 0. Whether x is 0 or 1. Similarly here, right? If x is 0, then we get this one would be 0 or 1 is 1. 1 or 0 is 1. The result is the same, which is 1. Lastly, it's about double complement, okay, double negation. This one is just equal to x, right? Okay. And then later on, we see about the truth tables. Again, right? We see that this is simple. Everyone know how to make it. Okay, truth table for a Boolean function, and or. This one is for a two variable function, right? X1 and X2 are the variables. When we have three variables, then the table size would be double, right? Having, right, 8 cases, right? 8 rows. Previously, it's just 4 cases, 4 rows. Now we have 8 cases. Okay. And then this table shows about the proof of the De Morgan theorem. That is, this one and this one are equivalent, right? Okay, moving on to more about the Boolean expression and function. Boolean, okay, consists of just only 2 possible values, 0 and 1. Okay, and then we may like consider many variables, xi, okay, xi. Here we see that I could be from 1, 2, 3 up to n, many of them. Okay. So xi is a Boolean variable. So a function, Boolean function, having n variables. That means Boolean function of degree n. Degree n. Okay. If we have 3 variables, then the Boolean function has degree 3. Let's see an example here. Consider a function of 2 variables, that is function of degree 2, xy is just x and y bar. Okay, that's given. Let's find out the value of f11. That means x is 1 and y is 1, right? So that just plug in to this function. So we have 1 and 1 bar. So that is 1 and 0 would be 0. F10 would be 1 and 0 bar. 1 and 1 is 1. Would be 0, 1 bar. So 0. Okay. Let me know if you have a different result. Okay, I might have some error here. 0 and 0. Right? Okay. So there is only one case that the result is 1. That is when x is 1 and y is 0. Starting with simple, just to make sure that our fundamental concept is good. Okay. Then if a Boolean function is given, we can construct a truth table, right? A corresponding truth table for the function. And then later, given a truth table, we are able to find the function, Boolean function as well, right? Okay, so let's complete this one together. That would x and y, right? So this means when x is 1 and y is 1, the result would be 1, right? Otherwise, just like 0 and 0, that's 0, right? 0 and 1 is 0. The z would be opposite from z bar. So we have 1, 0, 1 there. And then the last column, we do the AND of these two columns, right? The result, case by case, row by row. So we have 0 or 1 as 1, 0 or 0 is 0. Okay, so the result obtained in the rightmost column is very similar to Z bar. Okay, just only the last case here, that also 1, because this term is 1. Right? Okay. In the Boolean expression, okay, there could be many different operations. The simple ones are not, a negation, and or together. Okay, just like that we know about this already, right? And then the precedence, the order of the operation, right? Which one have to do first, second, third? Then we know that negation or not have to be done first. Okay, this have the first priority. Okay, first one, and this would be done next, right? Second, and this would be third. If they are together, right? So that we can see these three cases. Okay, similar to what we cover in the logic, right? The section logical expression, like in the earlier lecture, right? That is, we do the AND first for the first example here before we do the OR. And then this one, right? This is A bar, okay? Is the negation, A complement. That is not A. So that the order of operation is that we have to do the not A first before AND with the C, and so on, right? This one do the D bar negation first before AND with the B boy. And then lastly, the OR is performed. Okay, so now, right, it's just like a review. Moving on to the next section, which is about representing the Boolean functions. that we're gonna see about like sum of product expansions. Okay, but before that, let's start with simpler information first. Given a truth table for function f and g, shown here, find out the Boolean expression for each function. Boolean, can we? Given a truth table, considering function f first. Okay, function f is this one, right? It's a function of three variables, x, y, and z. So we just look at inside the table when the function is 1, right? When the function is 1, here. Function is 1. There is only one case, right? This one for the function f to be 1. And this happens when the input variables x is 1, right? Here. X is 1, y is 0, and z is 1. Here. Okay, that's from the table. So it means that for the function to be 1, x must be 1, y must be 0, and z must be 1. Okay, it's this one. Otherwise, the function is 0. So with this condition here, we can represent the function as x is 1, so we put x, okay, and y bar, and z. Okay. So we use we see that this just the expression of the condition that is right. X is 1, right, and y is 0, and z is 1 if then the function is 1, right? So that is x and y bar and z is f, x, y, and z. And okay, y is 0, so we make y bar. Okay. Why? Because when you substitute the variable with its value, this is 1, and 0 bar, and 1. 1 and 0 bar is 1, right? So you will get 1. So that's the function. Function would be 1. Okay. So basically, we can express the function as a product term, okay, product term of the variables that we have here, x, y, and z. The variable that is 1, then we just put the variable. If it is 0, we put the bar on the top, and then AND them all, then that's the expression here. let's try, let's make it for the function g as well. Okay, so I'm gonna delete this part to get room for the function g. Okay, function g. G, x, y, and z. This function is 1. Okay, when, where is it? This one and this one. There are two cases, right? This one, the first case, okay, let me, okay. G, x, y, and z is 1 when, for the first case, the function g is 1 when x is 1, right? X is 1, and y is 1, and z is 0. So we put bar on the top for the variable that is 0. So that when you substitute the value of each variable, that is x is 1, y is 1, and z is 0, you would get to 1. Okay, that is one case. And also the other case is this second case. This happens when x is 0, so we put x bar. And y is 1, so we just put y. And z is 0, so we put z bar. Okay, because of this one here. And then when you put 0, 1, 0, bar, then you will get 1 and 1 and 1. That is 1. Right? So that's the reason why each variable has to be presented. Okay. We haven't finished about the function g. Since there are two cases that g is 1, so we have to OR the two cases together, so that the result would be the g, x, y, z would be summation, Boolean sum of the two cases, x, y, z plus x, y. Right, so that's the result. Okay, so that we have to cover all the cases where the function is 1. Okay. What we just discussed is explained here as well as a definition that a Boolean variable, okay, like xi, it is called a literal, okay, literal, just one letter. And then the Boolean, the product term where we have all the variable xi together. Okay, Boolean, this one, this is a Boolean product, right? With, okay, n variables. Actually, this one, y. This one, Boolean product. Let me write it down. x1, x2, xn. Okay, we could have many variables, right? The min term of the Boolean variable is a product term. Okay, say min term is a product term with n variables. Okay, so that this product term would have the x1, x2, and so on there inside. Okay, just like, let's see this example first. I think it will be easier to understand before we go back to the definition again. Considering a min term, okay, min term is a product term, is equal 1, okay, if the variables are like this. Suppose x1 and x3 are 0, and the rest are 1s. That is for the min term to be 1. So that we can express the corresponding min term as a product term of the 5 variables having x1, okay, x2, x3, x4, and x5 together, like that. And then for the variables that having the value 0, okay, 0, which are x1 and x3, then we put the bar on the top. The other variables, they are 1s, so we don't have to do anything, just make it, just put it here, them here. So, and then n as a product term. So this is the min term. Okay. For a 5 variable function. Okay. We'll talk more about the min term later on. Okay, but now it's just we have to know that this is a product term with the number of variables equal to what we have for the function. Okay, if the function has 5 variables, then it will be something like this. But if it is a function of 3 variables, then the min term would have just only 3 variables inside. Okay. Sum of products expansion. What is it? In the next example. Sum of product means summation. Okay, the function is expressed as a summation like this, right? Summation of the product term. So this is product term number 1, number 2, number 3, something like this, right? For example, it could be like x or y. This is sum of product as well. But what about this one? In the example, this is not sum of product, but product of sum instead, right? Because it's the sum is in this term, and then it's and with the other term is the product term. So this is a product of sum. We can rearrange, okay, a given function, okay, make it as a sum of products. That would be the common form that people use, okay, people work on, sum of products, so that given the function, which is this one, okay, first we have to simplify, okay, expand the function as a sum of product first. So that is what we got here, right? By using the distribution law, we have this, right? So that is just like, okay, x and z bar, or y and z bar. Okay. So now this is a sum of products. But we want to have sum of products expansion. What is that? Okay. It means that each product term must have all the variables presented. Okay. This function, we have x, y, and z. All have to be in the product term, each product term. Okay. So how to make this expression so that each product term has all the three variables, x, y, and z. Okay. Then the result would be something like this. Okay. You see that each term is a product term having three variables, right? X, y, and z. Some having bar, some are not. Okay. So that's what we want. But how to get there? Okay. It is shown here that in order to have the three variables in each product term, we can do it, okay, using just the Boolean algebra. That is by, like here. In the next case, see that 1 is inside. Anything end with 1, right? A end with 1 is A, right? We know that. Because 1 means true. Anything end with true, it's just that value. Okay. So that we put the 1 there as the end. Why? Because we want to introduce a missing variable, which is y, inside, as shown here. Okay, so let me write down clearly. Okay, just considering the first term, x and z bar. Okay, you want to have y inside too, but how to preserve the original value expression here is the x and 1 and z bar, right? And this one could be y or y bar. Because A or A bar is just 1, right? True or false is true. and then expand out this one, then we get x, y, z bar, or x, y bar, z bar. So now we have our product terms, could be sum of product terms, okay, where each product term has 3 variables, x, y, and z. Okay, that's what happened here. So that the first 2 terms are the result from what we did here. The other term, y and z bar, okay, so we put 1 there so that we're gonna add x in. So x or x bar is 1, right? And then y and z bar. So that would be x, y, z bar, or x bar, y, z bar, right? And this one that we obtain is here. Okay, then we combine the 2 parts, and then we see that that is a duplicate of the first and the third term, right? This term and this term are the same. So A or A is A, right? So we just keep one term and remove the other term, a duplicate one. So that's the result. This is a sum of product expansion of the function f. Sum of products. Okay. Each product term consists of all the variables of the function x, y, and z. Okay. And then we know that there are corresponding Boolean laws, right here, the property. For the Boolean operation, okay, so now let's try another example to find the sum of products expansion for another function. A similar one, but not the same, x or y and z. This is x, y, or z bar. Okay, let's use a truth table as well. So x and y, actually from here, x and y, this one, right? It means that for this term to be 1, then it requires x to be 1 and y to be 1, both. So that it would be the case here. The 2 cases here. The rest would be all zeros, right? Right. So actually, this is the same function that we did previously, okay, earlier. Okay. How many cases that we have here? Ones, sum of products. One case, second one, third, fourth, fifth. There are 5 product terms here. Okay. For this term to be 1, okay, this would be when x is 0, y is this one, right? All x, y, and z are zeros. So we put bar on the top of each one. Okay. Consider the one next. It's 0, 1, 0. This is one when x, y, z. Put bar for x and z. Next one, x, y, z, 1, 0, 0. So we put bar for the y bar, for the y and the z. Next one, we could remove this. Okay. It's 1, 1, 0. So x, y, z. X is 1, y is 1, z is 0. So we put bar there. And the last one is all are ones. So no bar for any variable. Okay. So we see that each row, each case, considering when the this is 1, okay. That's the corresponding product term. And then we do the summation. Summation of these 5 product terms. Then that is the sum of products expansion. Okay. All right. Then let's move on to the next part, which is about duality. Okay. Dual form of a Boolean expression. So that is like given a function x, y, z. Okay. Is suppose. Okay, it's this one. Okay. Then we could find the dual of the function. Okay, suppose that the function here is just x, y, or 0, anything. This one. The dual can be obtained by interchanging the Boolean sum and Boolean product, and interchanging 0 and 1. So here we have x, y, or 0 as a function. Okay. Then the dual form would be equal to changing the and to be or, right? This, and then the y, and then this would be 1, but preserve the, the parenthesis there. So that we change the sign from and to be or, right? This sign. And 0 changing to be 1. So that's the dual form. Similarly, second case here, its dual form can be obtained, which is equal to here, x bar changing from and to or, and then 1 to 0, and then this or sign changing to be and. Right. Then that's what we got here. Okay, what is it for? Why we have to know this one, the dual form? It can be used to like prove some expression, or could give us a choice of representing a function. Okay. Let's see this example first. Okay. Considering a Boolean law, this one, which is an absorption law. Okay. Absorption law. This one, x and x or y is just equal to x. By doing the dual, then we have here x or y. Okay, dual of this one would be x or y, x and y, right? Changing the sign from and to or, and vice versa. And this is obviously equal to x, or we can see x and 1 or y. 1 or anything is 1, right? So it's just x. Okay, so that we can prove or verify the given statement if this is true or not by using the dual form. This is one way that we can do as well. The next example is given another Boolean expression or function here. Can we prove that this is true? We can simply, using the Boolean algebra, having all the laws, the properties, and to verify that the left-hand side and the right-hand side are equivalent. Right? Okay, just like we see here. So it takes a few steps to for the proof. Okay, that if we don't do any mistake, then we would get to the conclusion, yes, this is true. Okay, what about using the dual form of this one? Okay, from the left-hand side, okay, the dual of the expression would be just x1 bar, changing from or to and then x, hold on, and then this one would be changing from and to or, right? Just like that. And then the right-hand side, the dual of this one would be just x1, x2, and x2, right? From the left-hand side, then x1 bar, x1, x2, and bar, x2. We see that this term, maybe it's not clear. This term is just 0, right? True and false, false and true is false. So 0 and so we just have only this term left. And it's obvious that the left-hand side and the right-hand side are equivalent. So we finish the proof using the dual form. So that means the dual of this one, right? Dual of this one would be equal to the dual of this one. If yes, then we prove that the left-hand side and the right-hand side expressions are equal. Okay, and then, so we got to get familiar with the Boolean algebra, okay, using the properties, the laws as well. But that by doing that, we have to be quite careful, right? Very careful on putting the bar, the sign, and or not, something like that. Can we prove that this expression is valid? Okay, the left-hand side and the right-hand side are the same, are equal. There could be many ways, okay, that we can do, right? Taking a few steps to get to the result. Okay, more or less. Okay, but this one is, yeah, it's simple, right? You just do the distribution so that's what we got, right? So it's this term. The first inside here. And then the second term would be x1 bar and x3 and this one. Then we got here. And then check out if any term is 0 or 1, or we have a duplicate term or not. Okay. This term is 0. This term is 0, the first and the last term. Right? So that we have two terms left. And they are just the same as the given one. Okay. We can also use Venn diagram to prove or to verify if the given Boolean expression is valid or not, right? We know that. We have seen this. We talked about this in the previous lecture as well. Okay. Then let's move on to the next section, which is about logic gates. We talk about logic gate, AND gate, OR gate, NOT gate previously as well, right? And then we have function of the variables. So let's take a look at some components. When we put the gates together, forming a circuit, okay, digital circuit, simple ones that you're gonna have for the upcoming course as well about the digital circuit design or digital system design. The the small component inside the circuit. Here is a switch, okay, switch. On and off switch, binary switch. Okay. So that we have this one as a like open circuit. This is a closed circuit. So this is on, right? This is off. Okay. What does it mean by on? That electricity can go through the switch, like from left to right or from right to left, but not possible on the left-hand side here, right? Because it's open circuit. Okay. A symbol for a switch is here, just like a box. Okay. Binary switch. We could have a switch in a circuit, okay, having battery and light bulb here. Okay. So the two circuits are the same, right? They have the common ground. Okay. So this is ground, G and D. Right? So that this is plus minus. So the current go in this direction. Okay, and complete the loop. So when will the light be on? The light is a function of a switch X variable. Right? If X is 1, then the light would be on. So that if X is 1, the light would be on. If X is 0, the light would be off. So this is a function, okay, for this circuit. Fx is X. What about if we have two switches in parallel or in series? Then when will the light be on? Can we find out the function for the light? Light is a function of two variables, x1 and x2, right? 0 and 1. When will the light be on? So that the current can go through and complete the loop. This is when we have closed switches. That is x1 and x2 must be 1. 1 and 1. Otherwise, the light would be off. Okay, we need 1 here to be 1. If any of this is 0, then the result would be 0. So this is an AND function. The other one is a OR function. Okay, where we have a parallel configuration. When one of the x, okay, xi is 1, then if this is 1, then the current go in this direction and complete the loop, right? So the light is on, or it could be the other direction, this one, either one, or could be both. So this is x1 or x2. What about if we have combination of this circuit AND and OR together, series and parallel? When will the light be on? What is a function of this? Now we have x1, x2, and x3. For the light to be on, the current, x3 has to be 1, right? And this part have to be 1 as well. Inside, it could be x1 or x2, b1. So that's the function for this circuit. Okay, parallel and serial configuration, and or together. Inversion, what about we want to have our function fx is equal to not x or x bar. This is a corresponding circuit with just a switch in parallel with the light. So that, okay, the light could go here or the other one, the other side. So that is to have the light going through the current going through this one. Okay. That means the switch have to be off. That 0 here, and this would be 1. Or the other way around, if this is become 1, then this will become 0. Okay, so that's the function inversion. That is when the switch is on. Okay, when x is 1, it's 1. Switch is on. Then the light would be 0, be off. And then when x is 0, Lx would be 1, right? So that's how the NOT function performs. Okay, we know that the operation may have many variables included, right? So that the logic gate has many sides, right, to cover all the variables. And then, like putting them together, just and or operation, not operation, then we could have any circuit, okay, like here. We can find out the function for this circuit, right? Okay, which is equal to just simply this is x bar, x1 bar, this is x1 and x2, right? So the function here is x1 bar or x1, x2. Okay, we got that. And we can have a truth table for this function. The next one is about the waveform. Okay, waveform, that is very important here. What is it? That we have timing diagram. Okay, it's the waveform. So that along the x-axis is about time. Okay, time. Okay. Look at the truth table. We have 4 cases. Okay, so this would be what we have in the timing diagram, 4 parts of 4 sections. So this is section number 1, 2, 3, and 4. Okay, the values of the x1, x2, and so on are shown here. Like for the first case, both x1 and x2 are zeros. So this is the value here. Okay, second case, 0, 1. third case 1 0, next case 1 1. Okay, this just corresponds to what we have in the truth table. And then we can find out the result, okay, like from each gate as well, like from the NOT gate. Let's say we have, this is A and this is B, and then the final function is F, right? Okay. So that A is a NOT x1, right? A is equal to, right, x1 bar. So that 0 would be 1, 1. Just opposite. So that we see the line there, just 0 and 1 stage is shown, right? According to the value of the signal x1, x2, A, B, and F. x2, okay, A, all we have A. B is equal to x1 and x2, right? So that is, so 0 and 0, the result is 0. 0 and 1, result is 0. 1 and 0 is 0. And lastly, 1 and 1 is 1. And the function f, finally, is the OR of A and B, right? So that would be OR. 1 or 0 is 1. 1. 0 or 0 is 0. And 1. Okay. So we see that all the stages of the signal in the timing diagram are just according to the values in the circuit at each stage. Okay, there are 4 stages here. Right, that's how the waveform, the timing diagram is is presented. So that once you understand about like this circuit, you should be able to draw the timing diagram by yourself. Right? And vice versa, given a timing diagram, you are able to construct a truth table and finding out the corresponding Boolean expression for the circuit. Okay. Like that. Okay. And then just like this one, given a waveform, then we could find out the corresponding function and draw the circuit. And you can see that actually this circuit is equivalent to the previous one, but having less number of gates, fewer gates here. We have only one NOT gate and one OR gate, but the previous one we have AND gate as well. Okay, 3 gates total. Okay, so that we're gonna like consider about reducing, simplifying the function. Okay. The timing diagram here, later you're gonna measure the signals in like in the next course, in digital system design course. That will be a lab for you to play with, okay, with the logic gates as well. And then some equipment should be used like oscilloscope, logic analyzers, and also software to CAD to involve for the analysis and synthesis. Okay, synthesis means like could be optimizing, minimizing the or maximizing. Okay, change the result, the expression. But this can be done using the Boolean algebra, like here. This one, the left-hand side, can we prove that this is true? What about by just a Boolean algebra? Like we see that the left-hand side doesn't have the having just only x1 but no x2, right? So let's see. Left-hand side is okay x1 or x1 x2 would be equal to x1 x2 bar. We adding this is 1, right? 1 and anything doesn't change. A and 1 is A, right? So the second term still no change. And then expand out. So we have x1, x2 bar, x1, x2 plus x1, x2. Then we see that these two terms have x2, right? So that we can group this as x2, x1, or okay. So this would be just x2 and 1, right? And then we can do grouping here. Back it was x1 bar. So that's why we have x1 bar. Okay, that's right. So this is valid. This is true. So we see that the second term that we have here can be grouped, okay, with the third term, and also it can be grouped with the first term. Okay. In order to simplify the expression, okay, this is one way to do. All right. So now let's take a break. Yeah, it's about time. Yay. Okay, and then I will be back in 10 minutes. Okay? And then you can look at the exercise problem. But we have to come back for the remaining section as well today,นะคะ, to complete it. All right.